Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete history, design, and function of one of the most important safety innovations in automotive engineering, the automatic seatbelt retractor. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, focus, or fall asleep. There will be no sudden sounds, no music, and no emotional tone. Only the steady voice of information. Now, please sit back, close your eyes if you like, and let the story of the automatic seatbelt retractor begin. In the early 1960s, the automotive industry was undergoing a period of rapid growth and technological change, yet safety considerations were still in their infancy compared to today's rigorous standards. Automobiles were becoming faster, more powerful, and more widely available to the general public. But the infrastructure of safety technology had not caught up to the risks associated with modern driving. Seatbelts, though already known and in some cases installed in vehicles, were far from a universal or standardized feature. Many drivers and passengers viewed them as optional, inconvenient, or even unnecessary. It was in this context that the safety seatbelt patent of 1963 emerged as a transformative innovation. The concept of a safety belt was not new at the time, but the specific idea protected by the 1963 patent addressed several practical and technical shortcomings that had hindered the widespread adoption of seatbelts. Early designs often involved fixed-length straps that required manual adjustment before each use, leading many to simply ignore them. This created a paradox. The technology to save lives existed, yet the form in which it was presented was so inconvenient that it failed to fulfill its potential. The automatic retractor system, described in the 1963 patent, sought to bridge this gap between safety theory and everyday usability. By introducing a mechanism that could automatically retract and store the belt when not in use, and then extend it to a comfortable yet secure length when needed, the design aimed to eliminate one of the main psychological and functional barriers to consistent seatbelt use. The brilliance of this patent lay not only in the engineering details, but also in its understanding of human behavior. Drivers and passengers were far more likely to use a device that did not require a series of awkward manual adjustments every time they entered the car. The retractor system allowed the belt to be ready for immediate use, while keeping it neatly stored when not needed, avoiding the mess and inconvenience of loose straps hanging in the cabin. Moreover, the patent incorporated a safety locking feature that responded to sudden deceleration or collision forces, preventing the belt from extending further at the exact moment restraint was needed most. This mechanical foresight reflected a growing awareness in the engineering community of the physics of accidents and the importance of restraint systems that could adapt instantaneously to changing conditions. The timing of the 1963 patent was critical. In the United States and much of the industrialized world, growing public concern over rising traffic fatalities was beginning to influence both consumer attitudes and government policies. The publication of Ralph Nader's Unsafe at Any Speed, just 2 years later in 1965, would ignite public debate on vehicle safety. But innovations like the automatic retractor seatbelt were already laying the groundwork for a shift in industry practices. As a piece of intellectual property, the 1963 patent represented more than just a mechanical solution. It was a strategic step toward embedding safety into the everyday driving experience. By securing legal protection for the automatic retractor concept, the inventor not only safeguarded the commercial viability of the design, but also set the stage for its adoption across multiple vehicle models and brands. This, in turn, accelerated the normalization of seatbelts as a standard feature rather than an optional accessory. The implications of this innovation extended beyond individual vehicles, as automakers began to recognize the benefits of offering improved safety features. Competitive pressure encouraged others to follow suit, creating a cascade effect in the industry. The automatic retractor system became a blueprint for further refinements, influencing how engineers approached not only seatbelts, but also other restraint systems, including child safety seats and harnesses for specialized vehicles. In retrospect, the 1963 safety seatbelt patent can be seen as a turning point in automotive safety, not because it introduced the seatbelt itself, but because it solved the usability problem that had prevented seatbelts from achieving their life-saving potential. Its combination of mechanical elegance and human-centered design made it a cornerstone in the evolution of vehicle restraint systems. The journey from early, manually adjusted belts to today's sophisticated, sensor-driven restraint systems is a testament to the enduring impact of this innovation. The automatic retractor principle remains at the heart of modern seatbelt designs, albeit now enhanced with pyrotechnic pretensioners, force limiters, and integrated sensors. Yet the core idea that a safety device must be both effective and easy to use in order to be truly adopted remains as relevant today as it was in 1963. In this way, the safety seatbelt patent of that year occupies a unique place in the history of engineering. A relatively simple mechanical solution that reshaped industry practices, influenced regulatory standards, and ultimately saved countless lives by making safety a seamless part of the driving experience rather than an optional afterthought. The patent's legacy is one of bridging the gap between technical capability and everyday practicality, proving that innovation is not just about creating new mechanisms, but about ensuring they integrate naturally into human behavior. The early 1960s marked a transitional era in the automotive industry, where the fascination with speed, style, and affordability dominated public and manufacturer priorities, often overshadowing serious discussions about driver and passenger safety. Post-war prosperity had made car ownership accessible to a far larger portion of the population, and highways were expanding rapidly to connect cities and suburbs. Cars were symbols of freedom and status, with designers competing to create sleeker, more powerful models each year. However, behind the glamour and marketing campaigns lay a troubling reality. Traffic fatalities and serious injuries were on the rise, and the safety technology available in most cars was rudimentary at best. In many countries, including the United States, there were few government regulations requiring specific safety features, and what was offered often came as optional equipment that many buyers chose to forgo. Seatbelts, when available, were typically lap belts that required manual adjustment and offered limited protection compared to modern three-point designs. Airbags did not exist in production vehicles, crumple zones were not standard engineering considerations, and safety glass was often the most advanced feature one could expect. Public perception also posed a significant barrier to progress. Many drivers believed that seatbelts were uncomfortable, restrictive, or even dangerous, fearing that they might trap occupants in the event of a fire or submersion. Automakers, wary of scaring customers with reminders of the dangers of driving, downplayed the inclusion of safety equipment in advertising and focused instead on horsepower, chrome accents, and luxury interiors. It was in this environment that safety advocates began to push for reform, citing mounting evidence from accident statistics and crash investigations. Organizations such as the Insurance Institute for Highway Safety, founded in 1959, began publishing data that demonstrated the life-saving potential of restraint systems and other safety improvements. Internationally, some countries were beginning to take a more proactive stance. In Sweden, for instance, Volvo engineers were already experimenting with advanced seatbelt designs, leading to the introduction of the three-point seatbelt in 1959, a breakthrough that would influence global safety engineering for decades. Still, widespread adoption was slow, and in many markets, early innovations struggled to gain traction without regulatory pressure. The cultural and industrial backdrop of the early 1960s was therefore one of tension between the emerging awareness of vehicular danger and the inertia of established norms and consumer expectations. Media coverage of high-profile accidents, along with the work of pioneering safety researchers, began to shift the conversation. But significant change would not occur until public opinion was galvanized by influential publications and legislative action later in the decade. Within this context, patents like the 1963 automatic seatbelt retractor represented a critical bridge between theory and practice. By offering a solution that improved both the effectiveness and usability of seatbelts, such innovations provided tangible examples of how safety could be integrated into the driving experience without compromising comfort or style. The early 1960s also saw the beginnings of crash testing as a formalized process, with manufacturers conducting controlled collisions to study the effects on vehicle structure and occupants. These tests provided data that supported the development of features like retractable seatbelts, which could be fine-tuned to work in harmony with other elements of vehicle design. While the idea of building cars with safety as a primary design goal was still in its infancy, the seeds were being sown during this period. The historical context of the 1960s automotive safety landscape is therefore essential to understanding why the 1963 seatbelt retractor patent was so impactful. It was not just a mechanical innovation, it was a timely response to a growing but still hesitant movement towards safer vehicles. By addressing the functional shortcomings of existing seatbelts, it encouraged greater acceptance among both automakers and the public, helping to pave the way for the regulatory changes and cultural shifts that would follow later in the decade and into the 1970s. The inventor behind the 1963 automatic seatbelt retractor patent was a product of both the growing awareness of automotive safety and the engineering ingenuity of the post-war era. During this period, many mechanical engineers were either directly involved in the automotive industry or influenced by related fields such as aerospace and industrial machinery, where restraint systems and tension-controlled mechanisms were already in use. The individual or team responsible for this particular patent recognized a clear and pressing problem. Conventional seatbelts of the time required manual adjustment and were often left loose or unused entirely because they were inconvenient to put on and uncomfortable to wear for long periods. The invention process began with identifying the specific user behaviors and limitations of existing designs. Studies from insurance companies, safety advocates, and even limited in-house crash testing showed that a seatbelt's effectiveness depended on both proper positioning and adequate tension. Too loose, and the belt would allow the occupant to move dangerously forward in a crash. Too tight, and users might resist wearing it altogether. The inventor's challenge was to create a mechanism that could automatically retract slack while still allowing a degree of freedom for normal movement, a balance that required careful mechanical calibration. Filing the patent involved translating this practical vision into precise technical documentation. Patent applications of the era demanded detailed written descriptions of every component, its function, and how it interacted with the rest of the assembly. This included specifying the type and placement of springs, the geometry of the retractor spool, the locking mechanism's triggering conditions, and the method by which the system maintained consistent tension under different conditions. The drawings, which formed a key part of the submission, had to clearly depict both the assembled unit and sectional views that exposed internal parts, giving patent examiners and future engineers the means to fully understand and replicate the invention. The filing process also required demonstrating novelty and utility, meaning the inventor had to show how this design was different from and superior to prior seatbelt systems. This involved referencing earlier patents and explaining their shortcomings, such as the lack of automatic retraction, the absence of reliable locking under sudden deceleration, or the need for constant manual adjustment. By contrasting these older designs with the proposed mechanism, the inventor established a clear case for the innovation's unique value. The legal aspect of filing a patent was as important as the engineering one. The inventor likely worked with a patent attorney or specialist to ensure the claims were broad enough to protect against competitors producing functionally identical systems, yet specific enough to meet the patent office's requirements. This balance could determine whether the design became a lasting standard or was easily bypassed by slight variations. In 1963, the United States Patent Office was already dealing with an increasing number of automotive-related submissions, as manufacturers and independent inventors alike raced to secure intellectual property in a rapidly evolving market. Once submitted, the patent application entered a review process in which examiners assessed the clarity of the documentation, the legitimacy of the novelty claims, and the overall feasibility of the design. If any issues arose, the inventor had the opportunity to amend the application or provide additional supporting material. Approval of the patent not only granted legal protection for a set period, but also served as a formal acknowledgement of the invention's originality and technical merit. For automotive suppliers and manufacturers, securing such patents was not only a matter of protecting engineering work, but also of establishing credibility and competitive advantage. In the case of the 1963 automatic seatbelt retractor, the patent positioned its inventor as an innovator at the forefront of safety technology. Once granted, the patent could be licensed to manufacturers or directly integrated into vehicle production, setting the stage for widespread adoption. The filing process, therefore, was not just a bureaucratic step, but an essential bridge between the conceptual stage of the invention and its real-world implementation. Without it, the design could easily have been copied without recognition or reward for its creator, and its contribution to automotive safety might have been diluted or delayed. In the early 1960s, before the introduction of the automatic seatbelt retractor patent, the majority of seatbelt systems in automobiles were simple static webbing straps anchored at fixed points on the car's structure. These belts typically required the user to manually grasp the free end of the webbing, pull it across their torso, and fasten it into a buckle that latched to a stationary anchor on the opposite side. Once secured, the belt's length remained fixed unless the user manually adjusted it again. This rigidity in design created multiple problems in both safety performance and user compliance. The first issue was slack management. A seatbelt that was too loose significantly reduced its effectiveness in restraining the occupant during a collision. Excess slack allowed forward movement of the body, which in turn increased the risk of striking the steering wheel, dashboard, or windshield. On the other hand, a belt that was adjusted too tightly was uncomfortable, restricting breathing and movement, which discouraged people from wearing it consistently. Many drivers and passengers preferred to leave belts loose for comfort, inadvertently compromising safety. Another key problem was the inconvenience of adjustment. Fixed-length belts often required manual repositioning for each different user. If multiple people shared the same vehicle, every change in driver or passenger meant adjusting the belt length by feeding the webbing through a friction buckle or similar hardware, a process that could be awkward and time-consuming. This inconvenience led to a significant number of people simply choosing not to wear seatbelts at all, especially on short trips. In addition to these user-related factors, older seatbelt systems lacked dynamic response to sudden changes in motion. In a collision or abrupt deceleration, a properly tensioned belt would hold the occupant in place, but belts that had loosened over time or during movement failed to provide the necessary restraint. There were also instances where belts would shift or slip in their buckles during the course of a trip, creating dangerous levels of slack just when restraint was most needed. The static belts of the period also posed a challenge for maintaining an optimal position across the occupant's body. If a belt was improperly positioned, too high across the abdomen or too close to the neck, it could cause serious injury in a crash by concentrating force on vulnerable areas. Without a mechanism to maintain both correct tension and positioning, comfort adjustments often led to unsafe placement. Furthermore, early belt materials, while durable, did not have the same refined weave and flexibility as later designs. Combined with the fixed anchor points, this could result in belts that dug into the body during everyday driving, further discouraging their use. The problem was not just technical, but behavioral. Even when safety campaigns of the era encouraged the use of seatbelts, many motorists resisted, citing discomfort, the hassle of manual adjustment, or a belief that belts were unnecessary for skilled drivers. This combination of poor usability and limited adaptability meant that even when belts were installed in vehicles, they were far from being used consistently or correctly. From an engineering standpoint, the lack of an automatic retraction system also allowed belts to become tangled, caught in doors, or left hanging loosely, which increased wear and reduced their functional lifespan. The introduction of a mechanism that could automatically adjust for comfort and safety while keeping the belt neatly stowed was a direct response to these persistent issues. The 1963 automatic retractor patent targeted all these shortcomings at once, aiming to increase compliance, improve safety, and extend the belt's operational life. The automatic seatbelt retractor system, described in the 1963 patent, introduced a compact yet highly effective mechanism that fundamentally changed how seatbelts operated in vehicles. At its core, the system consisted of a spool mounted within a housing, around which the webbing of the seatbelt was wound. The spool was mounted on an axle that allowed it to rotate freely under normal conditions, enabling the belt to be extended or retracted as needed. The retraction was powered by a coiled flat spring, often referred to as a spiral or clock spring, which stored potential energy when the belt was pulled out and released that energy to rewind the belt onto the spool when tension was no longer applied. This simple but elegant design allowed the belt to automatically retract when not in use, keeping it neatly stowed and preventing tangles or obstructions. The retractor housing also incorporated a braking or locking mechanism that activated under specific conditions, such as sudden deceleration or rapid movement of the belt. In most designs of that era, this locking function was achieved through a centrifugal clutch or a pendulum-based sensor. The centrifugal type relied on the increased rotational speed of the spool during a sudden pull, which would engage a set of locking pawls against a toothed gear attached to the spool, preventing further payout of the webbing. The pendulum type used a small weighted element suspended inside the housing, which would swing forward under rapid deceleration, triggering the locking mechanism in a similar manner. The 1963 patent placed significant emphasis on achieving a balance between free movement for comfort and quick locking for safety. The retraction force generated by the spring had to be strong enough to take up slack and maintain a snug but comfortable fit, yet not so strong that it caused constant pressure on the occupant's body. This balance was achieved by carefully selecting the spring's material, width, thickness, and number of coils. In addition to the spring and locking mechanism, the retractor assembly included guide slots and rollers to ensure smooth feeding of the webbing onto and off of the spool. This prevented twisting and abrasion, both of which could weaken the belt over time. The patent also detailed the use of a pre-tensioning feature, not in the modern explosive sense, but in the form of an initial bias that kept the belt slightly retracted even when worn, ensuring it stayed properly positioned without noticeable slack. Another important mechanical aspect was the modularity of the design. The retractor could be installed in various orientations within the vehicle, making it adaptable for use in both front and rear seating positions. This allowed automotive manufacturers greater flexibility in designing interiors without compromising the belt's function. The materials specified for the housing and spool were chosen for both strength and resistance to wear, often involving stamped or cast metal components combined with low-friction bushings. The overall assembly was intended to be durable enough to last the life of the vehicle without requiring maintenance, apart from occasional inspection. In essence, the automatic retractor system solved three key problems simultaneously. It eliminated the inconvenience of manual belt adjustment, ensured optimal tension at all times for both safety and comfort, and kept the belt neatly stored when not in use. By integrating these functions into a compact, self-contained unit, the 1963 design represented a major leap forward in occupant restraint technology and set the stage for many refinements in the decades that followed. The spring was the heart of the 1963 automatic seatbelt retractor system, and its behavior determined both the comfort and safety of the occupant. The design relied on a flat spiral spring housed within the retractor casing, a form chosen for its ability to store a large amount of energy in a compact space while delivering a smooth and predictable force. This spring was anchored at one end to the stationary housing and at the other to the rotating spool on which the seatbelt webbing was wound. When the belt was extended, the spool rotated and wound the spring tighter, storing potential energy. Once the occupant released tension on the belt, the spring unwound, rotating the spool in the opposite direction and retracting the belt. The patent described the critical need to calibrate the spring's torque so that the retraction force was strong enough to take up slack, but not so aggressive as to create constant and uncomfortable pressure on the user's torso. This was achieved by careful selection of the spring's material composition, thickness, width, and the number of coils. For example, using tempered spring steel provided the resilience needed to maintain performance over thousands of cycles without fatigue. The geometry of the spring housing was also important, ensuring that the coils unwound smoothly without binding or uneven force distribution. Tension control in the system extended beyond simply retracting the belt. The patent emphasized the importance of maintaining a consistent baseline tension on the webbing during use. This was done to keep the belt close to the body without gaps, which could allow excessive forward movement during a crash, while also preventing the belt from becoming too tight during normal driving. The spring's preload, or the initial amount of tension applied even when the belt was fully retracted, was a crucial factor in achieving this balance. Some designs incorporated a small friction brake or damping element to slow the retraction speed. This prevented the belt from snapping back into the housing, which could damage the belt edges or cause discomfort to the user. In the 1963 design, such control could be achieved by adding a felt or fiber pad against the side of the spool, or by using low-friction bushings that introduced just enough resistance to smooth the motion without interfering with the belt's availability in an emergency. Additionally, the interaction between the spring and the locking mechanism had to be precisely coordinated. When the locking device engaged during a sudden deceleration, the spring's stored energy would be prevented from retracting the belt further, effectively holding the occupant in place. If this coordination was off, the belt could lock prematurely or fail to lock when needed. The patent made note of the tolerances necessary to ensure reliable operation under a range of environmental conditions, such as extreme cold, heat, or humidity, all of which could affect the elasticity and performance of the spring material. Over the lifetime of the vehicle, the spring was expected to retain its mechanical properties, despite thousands of extensions and retractions. This durability requirement influenced not only the choice of material, but also the heat treatment processes applied during manufacturing. Protective coatings could be added to prevent corrosion, further extending the operational life of the retractor system. Ultimately, the role of the spring in the 1963 automatic seatbelt retractor patent was not limited to pulling the belt back into its housing. It was a carefully engineered component that ensured the right amount of tension at all times, allowed for user comfort, contributed to the system's readiness in an emergency, and maintained reliability over years of service. Without the precision in its design and calibration, the entire retractor mechanism would fail to meet the safety goals that made the invention so significant. The locking mechanism, described in the 1963 automatic seatbelt retractor patent, was the critical safety feature that transformed a simple retraction device into a life-saving restraint system. Its purpose was to detect sudden deceleration, such as that experienced in a collision, and instantly prevent the belt from extending any further, holding the occupant securely in place. The mechanism operated through a combination of mechanical sensing and direct engagement with the retractor spool. At the core of this system was an inertia-based trigger, often realized as a weighted pendulum or a centrifugal clutch. Under normal driving conditions, the spool was free to rotate as the occupant leaned forward or shifted position, with the spring providing gentle retraction force. However, in the event of rapid deceleration, the sudden change in motion caused the pendulum or clutch to move out of its neutral position. This movement would force a locking pole into engagement with a toothed gear or ratchet attached to the spool, stopping its rotation instantly. The patent emphasized that the sensitivity of the inertia mechanism had to be carefully calibrated. If the system was too sensitive, it could lock the belt during minor movements, creating annoyance for the occupant and discouraging proper belt use. If it was not sensitive enough, the belt might fail to lock during the initial milliseconds of a collision, allowing excessive forward movement before restraint began. Achieving the correct balance involved selecting the right mass and geometry for the pendulum or clutch components, as well as designing precise pivot points and return springs to reset the mechanism after activation. Another important consideration in the design was reliability across a wide range of environmental conditions. Temperature changes could affect lubrication viscosity, and dust or debris could interfere with the movement of the locking components. The patent described protective housings and the use of corrosion-resistant materials, such as plated steel or specific alloys, to ensure long-term function. Additionally, the locking mechanism had to integrate seamlessly with the tension control system described in earlier sections. During normal retraction, the spring applied a consistent pull on the belt, but in a lock event, the pole and gear interface had to withstand the full force of the occupant's momentum without slipping or breaking. This meant that the teeth of the locking gear had to be deep and sharply defined, and the pole had to be made from a hardened material capable of resisting deformation under extreme loads. The engagement between the pole and gear also needed to be immediate, with minimal free play, to avoid any lag in the restraint function. The 1963 design allowed the locking mechanism to reset automatically once the deceleration event ended and the occupant's movement stabilized. This reset function was critical for making the belt usable immediately after a sudden stop or minor impact, avoiding the need for manual intervention. In the broader context of automotive safety, the introduction of such a locking system represented a significant step forward. Before this patent, many seatbelt designs relied solely on manual adjustment or constant tension, which could not adapt quickly enough to an emergency situation. By incorporating an inertia-triggered lock into the retractor system, the inventors created a belt that could remain comfortable and unobtrusive during everyday driving, while becoming rigidly secure in the fraction of a second when it was needed most. This concept has endured in modern vehicles, where more advanced versions of inertia locks, often combined with electronic sensors, continue to protect occupants during accidents. The 1963 patent laid the foundation for these innovations, demonstrating that safety, comfort, and practicality could be achieved in a single mechanism. The 1963 automatic seatbelt retractor patent dedicated significant attention to the selection of materials and the durability of each component, recognizing that reliability over time was essential for a safety device intended to perform flawlessly under extreme conditions. The patent's description emphasized that every part of the retractor system, from the belt webbing itself to the smallest spring or locking pole, had to be manufactured from materials capable of resisting wear, corrosion, and fatigue. For the belt webbing, woven synthetic fibers such as nylon were highlighted as ideal choices because of their high tensile strength, resistance to stretching, and ability to retain structural integrity even after prolonged exposure to sunlight, moisture, and fluctuating temperatures. Unlike natural fibers, which could rot or degrade over time, nylon offered consistent performance, ensuring that the restraint force during a collision would be transmitted directly to the occupant's body without failure. The retractor housing and frame were specified to be constructed from corrosion-resistant metals, with steel alloys being the preferred option due to their balance of strength, machinability, and cost-effectiveness. In environments where the system would be exposed to road salts, humidity, and temperature extremes, protective surface treatments such as zinc plating or chromate coatings were recommended to prevent rust and maintain smooth mechanical operation. For moving parts like gears and pulleys, the patent suggested the use of hardened steel or high-grade bronze alloys. Hardened steel provided exceptional wear resistance for teeth and contact surfaces, while bronze offered lower friction and self-lubricating properties in certain applications. These material choices were essential for ensuring that the retractor would continue to function smoothly, even after thousands of extension and retraction cycles. Springs, which played a central role in maintaining belt tension and operating the locking mechanism, required precise material selection to avoid loss of elasticity over time. The patent proposed using tempered spring steel, which could endure constant flexing without significant fatigue. Additionally, protective coatings or encasing the springs within sealed compartments helped shield them from dust, dirt, and moisture, further extending their service life. Lubrication was another key factor in the durability strategy. The patent recommended the application of stable, long-lasting greases that would not degrade into sticky residues or lose viscosity at extreme temperatures. The choice of lubricant was particularly important for the locking mechanism's moving parts, as any binding or sluggish response could compromise safety during a sudden deceleration. The designers also considered the effects of repeated mechanical shocks and vibrations, which could loosen fasteners or cause gradual wear. To counter this, locking nuts, precision rivets, and interference fit components were specified for critical joints, ensuring that parts would remain securely fastened throughout the life of the device. The durability considerations extended beyond mechanical components to include resistance to chemical exposure. Automotive interiors often contain cleaning agents, fuel vapors, and off-gassed chemicals from plastics, all of which could potentially degrade materials. The patent emphasized the need for testing material compatibility to ensure that neither the webbing nor the metal parts suffered from weakening or discoloration over years of service. Overall, the focus on materials and durability in the 1963 patent reflected an understanding that a safety device's effectiveness depended not just on its design, but on its ability to maintain that design's performance over decades of use. The choices outlined in the document provided a blueprint for modern manufacturers, many of whom still follow the same fundamental principles today, albeit with updated materials and manufacturing techniques. The 1963 automatic seatbelt retractor patent dedicated significant attention to the selection of materials and the durability of each component, recognizing that reliability over time was essential for a safety device intended to perform flawlessly under extreme conditions. The patent's description emphasized that every part of the retractor system, from the belt webbing itself to the smallest spring or locking pawl, had to be manufactured from materials capable of resisting wear, corrosion, and fatigue. For the belt webbing, woven synthetic fibers, such as nylon, were highlighted as ideal choices because of their high tensile strength, resistance to stretching, and ability to retain structural integrity even after prolonged exposure to sunlight, moisture, and fluctuating temperatures. Unlike natural fibers, which could rot or degrade over time, nylon offered consistent performance, ensuring that the restraint force during a collision would be transmitted directly to the occupant's body without failure. The retractor housing and frame were specified to be constructed from corrosion-resistant metals, with steel alloys being the preferred option due to their balance of strength, machinability, and cost-effectiveness. In environments where the system would be exposed to road salts, humidity, and temperature extremes, protective surface treatments, such as zinc plating or chromate coatings, were recommended to prevent rust and maintain smooth mechanical operation. For moving parts like gears and pulleys, the patent suggested the use of hardened steel or high-grade bronze alloys. Hardened steel provided exceptional wear resistance for teeth and contact surfaces, while bronze offered lower friction and self-lubricating properties in certain applications. These material choices were essential for ensuring that the retractor would continue to function smoothly even after thousands of extension and retraction cycles. Springs, which played a central role in maintaining belt tension and operating the locking mechanism, required precise material selection to avoid loss of elasticity over time. The patent proposed using tempered spring steel, which could endure constant flexing without significant fatigue. Additionally, protective coatings, or encasing the springs within sealed compartments, helped shield them from dust, dirt, and moisture, further extending their service life. Lubrication was another key factor in the durability strategy. The patent recommended the application of stable, long-lasting greases that would not degrade into sticky residues or lose viscosity at extreme temperatures. The choice of lubricant was particularly important for the locking mechanism's moving parts, as any binding or sluggish response could compromise safety during a sudden deceleration. The designers also considered the effects of repeated mechanical shocks and vibrations, which could loosen fasteners or cause gradual wear. To counter this, locking nuts, precision rivets, and interference-fit components were specified for critical joints, ensuring that parts would remain securely fastened throughout the life of the device. The durability considerations extended beyond mechanical components to include resistance to chemical exposure. Automotive interiors often contain cleaning agents, fuel vapors, and off-gassed chemicals from plastics, all of which could potentially degrade materials. The patent emphasized the need for testing material compatibility to ensure that neither the webbing nor the metal parts suffered from weakening or discoloration over years of service. Overall, the focus on materials and durability in the 1963 patent reflected an understanding that a safety device's effectiveness depended not just on its design, but on its ability to maintain that design's performance over decades of use. The choices outlined in the document provided a blueprint for modern manufacturers, many of whom still follow the same fundamental principles today, albeit with updated materials and manufacturing techniques. Modern seatbelt retractor systems represent decades of incremental improvement over the foundational 1963 design, yet the core mechanical principles established by that patent remain clearly recognizable in contemporary models. The automatic retractor concept, introduced in the early 1960s, relied primarily on a spring-loaded spool that maintained constant tension on the belt, allowing it to retract smoothly when not in use and to extend effortlessly when needed. Today's systems still employ spools and tension springs, but they are often enhanced with advanced materials, precision manufacturing techniques, and integrated electronics that improve performance and adaptability. One of the most significant differences between the original and modern designs is the inclusion of pretensioners, which use pyrotechnic or mechanical actuators to rapidly tighten the belt in the first milliseconds of a collision. This feature builds upon the automatic retraction mechanism, but adds an active safety layer that helps position the occupant more securely before the peak crash forces occur. The 1963 patent did not include this function, as the technology and understanding of crash dynamics were not yet advanced enough to implement it. But without the original retractor's reliability and consistency, pretensioners would not have been as practical to integrate. Another major development is the use of load limiters, which allow the belt to extend slightly under extreme force, reducing the risk of injury to the occupant's chest and rib cage. This balancing act between restraint and controlled movement was not present in the early designs, which were more rigid in their locking behavior once engaged. Modern retractors also tend to feature dual sensor locking mechanisms, combining vehicle deceleration sensors with belt webbing movement sensors to provide faster and more precise locking in various crash scenarios. This dual trigger approach is an evolution of the simple inertia-activated locks described in the 1963 document. Material science has also contributed to the differences between past and present. Early retractors used metal components that, while durable, could be heavier and more prone to wear in certain areas. Contemporary retractors often employ lightweight alloys, high-strength plastics, and treated surfaces that reduce friction and resist corrosion, significantly extending their service life. The belt webbing itself has changed as well, with modern fibers offering higher tensile strength, better abrasion resistance, and flame retardant properties, all of which enhance the system's overall safety. Ergonomics and user comfort have also evolved. Early retractors could sometimes create excessive belt tension when occupants shifted in their seats, leading to discomfort on longer drives. Modern designs employ advanced tension control systems that allow for a small amount of slack during normal movement, but tighten instantly when needed. This balance of comfort and safety encourages consistent use, something the original design aimed to achieve, but could only partially realize with the technology of its time. The integration of modern retractors into a vehicle's overall safety ecosystem is another clear point of divergence. Today, seatbelt systems are linked to airbag deployment algorithms, seat occupancy sensors, and even driver assistance systems, creating a layered safety network. The retractor becomes not just a standalone mechanical device, but part of a coordinated system that can adjust its behavior based on crash severity, occupant size, and seating position. Despite all these advancements, the mechanical simplicity and elegance of the 1963 automatic retractor remain evident in every modern version. The core principles of automatic adjustment, secure locking during sudden deceleration, and durability under repeated use are as relevant now as they were over 60 years ago. The difference lies in how these principles are implemented, with modern systems using a blend of precision engineering and digital intelligence to achieve even greater levels of protection. When compared directly, it is clear that modern retractors are more capable, versatile, and comfortable, yet they owe their very existence to the original breakthrough of making seatbelts a self-adjusting, user-friendly safety feature. The automatic seatbelt retractor system, described in the 1963 patent, not only transformed vehicle safety in the United States, but also served as a foundation for global adoption and adaptation in the decades that followed. In the years immediately after its introduction, several major automotive manufacturers in Europe and Japan began incorporating similar mechanisms into their vehicles, either through licensing agreements or by developing their own variations based on the same core mechanical principles. Countries with strong safety advocacy movements, such as Sweden, which was already pioneering seatbelt integration through companies like Volvo, quickly embraced the technology as part of broader initiatives to reduce road fatalities. The appeal of the automatic retractor lay in its ability to combine safety with convenience, a factor that greatly improved public acceptance of seatbelts at a time when their use was still optional in many regions. As international safety regulations evolved, particularly during the 1970s and 1980s, various governments began to mandate seatbelt use, and this in turn accelerated the global standardization of the retractor system. However, these mandates also introduced regional variations. In some countries, retractor systems were adapted to meet specific climate or durability challenges, such as resisting extreme humidity in tropical environments or ensuring smooth operation in sub-zero temperatures in northern climates. Materials, spring tensions, and locking mechanisms were sometimes modified to suit local driving conditions and manufacturing preferences. Japan, for instance, became known for producing highly compact retractor units that could be integrated seamlessly into smaller vehicle cabins without sacrificing performance. In Europe, certain manufacturers experimented with dual-stage locking systems that offered both gradual and immediate locking, depending on the severity of deceleration. Over time, the basic design also inspired innovations beyond passenger vehicles. Variations of the retractor mechanism began appearing in buses, aircraft, trains, and even in specialized equipment such as construction machinery and agricultural vehicles. These adaptations often required stronger springs, reinforced housings, or alternative mounting configurations, but they all retained the essential functionality of automatic retraction combined with instant locking under dangerous conditions. International collaboration played a significant role in refining these systems. Engineers from different countries often shared testing data, crash analysis results, and durability studies, leading to subtle but important improvements in the design. By the 1990s, retractor technology had become so widespread that it was no longer seen as a competitive advantage, but rather as a baseline expectation for any vehicle sold in regulated markets. As safety awareness grew globally, some countries introduced public campaigns highlighting the benefits of seatbelts with automatic retractors, further embedding the technology into everyday life. The cultural acceptance of seatbelts, which had once faced resistance, was now supported by decades of proven performance and comfort. The global spread of the 1963 concept also paved the way for integrating electronic components into retractors, allowing for new safety features that could be tailored to local laws and driving habits. For example, in certain European markets, seatbelt reminders became mandatory, and these systems worked in tandem with the retractor to encourage proper usage. In countries with high accident rates, manufacturers sometimes calibrated the locking mechanisms to be more sensitive, ensuring faster engagement during rapid maneuvers. Ultimately, the adoption of the automatic seatbelt retractor system on a global scale demonstrates how a single mechanical innovation can transcend its original market and influence safety standards across cultures and industries. While modern implementations may vary in materials, design refinements, and integration with advanced safety systems, the original 1963 patent remains a clear ancestor to virtually every seatbelt retractor in use today. Its legacy reinforced every time a driver hears the familiar click of a belt locking into place before a journey begins. The 1963 automatic seatbelt retractor patent stands as one of the most influential milestones in the history of automotive safety engineering. Its core innovation, a self-retracting belt mechanism capable of instant locking during sudden deceleration, bridged the gap between safety and user convenience at a time when public adoption of seatbelts was far from universal. Before its introduction, seatbelts were often seen as cumbersome, uncomfortable, and even unnecessary by many drivers and passengers. The retractor changed this perception by allowing the belt to remain comfortably slack during normal movement, while ensuring it would lock immediately in an emergency. This simple yet transformative improvement greatly increased compliance rates among vehicle occupants, which in turn contributed to measurable reductions in injury severity and fatalities in traffic accidents. From a technical standpoint, the legacy of the 1963 design lies in its enduring mechanical principles. While modern systems now incorporate electronic pretensioners, load limiters, and integration with airbag deployment sequences, the fundamental mechanism of controlled retraction, paired with instantaneous locking, remains essentially unchanged. This persistence is a testament to the robustness and efficiency of the original concept. Even with advances in materials science, crash sensing, and manufacturing methods, The core functionality envisioned in the early 1960s still defines seatbelt operation more than 60 years later. The retractor's influence also extends beyond automobiles. Variants of the mechanism have been adapted for use in aviation, public transportation, heavy machinery, and specialized safety harnesses in industrial settings. These adaptations have further reinforced the patent's legacy, proving that the design is not just a solution for passenger vehicles, but a versatile safety technology applicable to multiple industries. In regulatory terms, the 1963 invention helped pave the way for global seatbelt mandates. By making seatbelts easier and more comfortable to use, it reduced the barriers to legislative action. Governments found it easier to promote and enforce seatbelt laws once the technology no longer imposed significant discomfort or inconvenience on drivers and passengers. In cultural terms, it helped transform seatbelt usage from a niche safety choice into a universal habit. Over time, what began as an engineering solution became a silent, daily ritual for billions of people worldwide, so ingrained that it often goes unnoticed. Every click of a belt locking into its buckle is, in part, a tribute to the ingenuity of the original design. Today's safety engineers still study the 1963 retractor when developing new restraint systems, not because they seek to replicate it exactly, but because it represents a perfect example of how a well-engineered mechanical system can achieve lasting relevance. The patent's combination of simplicity, reliability, and adaptability makes it a benchmark for practical engineering solutions. Its success also offers a valuable lesson. Innovations that encourage user acceptance can be as critical to saving lives as the technical performance of the safety device itself. The legacy of the 1963 automatic seatbelt retractor is therefore not just about mechanical ingenuity, but about the profound human impact of thoughtful design. It reshaped the relationship between people and safety technology, demonstrating that the best engineering solutions work seamlessly in the background, protecting without intruding, and becoming so reliable that their presence is taken for granted. Even in an era of autonomous vehicles, advanced driver assistance systems, and integrated crash avoidance technologies, the humble seatbelt retractor remains a core element of occupant protection, proving that true engineering excellence is timeless.